Good morning, students. We are going to take you on calculus this semester, and I hope some of you have met in M1511. If that's the case, that's good to meet you again here on this course. So you're welcome, all of you, those who are new, those who have been with on M1511, you're all welcome into this course. But few things to highlight before we start the course. The first one is that the course outline has already been uploaded online on Tutor. Please have time to look at the course outline. And inside the course outline, you will see the topics that we are going to cover this semester, starting from the limits all the way to the application of integration. Another point is that we will have 3 sessions, lecture sessions, where we'll meet online. Probably we will upload some material in advance, and during that time we expect you to be online and interact with the material. And then you keep your questions for Friday. On Friday we'll have a 2-hour session of a tutorial where we plan to come to the chat room online, and then you ask all the questions that you had after interacting with the materials during the week. And then we'll try as much as possible to address your questions, although your number could be large, but we will see as we go along how we plan it and how we try to manage it and make it better. The other point which I touched but is the issue of material. We will upload material probably in the form of a video like we do sometimes, especially for some of the topics which are challenging. We will also upload material in the form of a PowerPoint. And sometimes we'll take material from a text from some books which we're interested in or a section, and then upload it on Tutor, probably with some exercises. So prepare yourself to work through the exercises as much as you can and try to interact with the material and understand the material. So having said this, I think we should straight away start. So the first topic which we are going to look at is limit. And we want to know what is the limit of a function. What is the limit of a function? So we will look at the limit of a function, try to build up an informal definition of the limit of a function, looking at some numerical values from a table, and try to estimate or guess the limit from there. And also we'll look at it from the graph and try to guess the limit from there. So in this way, we hope by the end of this lecture, you will be able to guess the limit or be able to find the limit, although with some kind of informal definition. So straight away, let's start with numerical, where we start with the table. Suppose someone is giving you a function of this form, and you are asked to study the behavior of the function around a point. In this case, we are looking at the point x is equal to 1. And one thing that is obvious, there are 2 sides to the point 1. We can have values which are less than 1, or we can have values which are greater than 1. We are not interested at 1 at the moment, at x is equal to 1 at the moment. We are just looking at in the neighborhood of 1, or as we get closer and closer to 1. So the main idea of a limit is to study the behavior of the function as you use the values of the x, which is our variable in this case, around 1. So suppose we take values which are less than 1, where we'll say we are approaching 1 from the left. So you start somewhere. In this case, we start from 0.5. Somebody could start somewhere else. But what is important is to approach 1. So keep taking your values and get as close as possible to 1. And take those values, like you take 0.5, evaluate the values into the function f of x, and then you will get the values of f of x. The first one, when you have 0.5, you get 0.666667, and you use 0.9 also, you take it and then evaluate into the function. Then as you continue all the way down, you get the behavior of the function as you approach this function from the left. And you can see the values of the function now approach 0.5. So we can make some kind of a bit of a bad conclusion, probably, or an early conclusion, that with this function that we have, as the values of x approach 1 from the left, the behavior of the function or the values of the function approach 0.5. So we can leave that guess as it is and then go to the right. So now let's pick the values which are greater than 1, which is the right of 1. In this case, we decided to start with 1.5. So you take 1.5, you plug it into the function, you evaluate that, you get 0.4, and then you also continue like you did with the left by approaching 1. That means you are getting as close as possible to 1, and then on the right you study the behavior of your function, find that the function again in this case approaches 0.5. Interesting. And you can see, even by looking at the last value here of the function, it gets closer and closer and closer to 0.5. So we can guess that the limit of this function as we approach from the right is 0.5. That's a guess. So one thing which you should bear in mind, especially in this case, is that we get the same limit as we approach from the left and also as we approach from the right. So you can see we get 0.5 from the left and also from the right. That thing is very important, which we'll talk about later, because it tells us about the existence of the limit. If we can get the same value from as we approach from the left and also as we approach from the right, we will conclude that the limit of the function, in this case as x approaches 1, is 0.5, and we will say the limit exists. If we can get two different values, we will say the limit of this function as we approach 1 does not exist. So that's why we said you should bear that in mind. So that's the conclusion we take from this example. Now let's look at the same example from the graph. We want to study the behavior again, but now looking at the graph. And you can see you have a function here, and then somebody has already done a good job, has already plotted it for us. So let's say you approach 1 from the left, where you are taking the values of x. Let's start somewhere far from 1. You go to the graph, and then you find the value of f. You will find that it's a bit not so close to 0.5. In this case, we have drawn 0.5 so that you can see clearly. And then you take another value, you try to get closer to 1. So let's take the next value, and then you try to find f. You find that f is getting closer to 0.5. That is from the left. And let's try to to do the same thing from the right. Start somewhere far, you take this value, you go to the graph, and then you find the value of f of x. Don't mind my bad drawing, I think you can do better. You'll find that from the right, now as you start, you're still a little bit far from 0.5. If we take the next value, probably closer to 1 of x, and then check f of x, you find that it gets closer to 0.5. So that's the idea. Then we can conclude that approaching f of x, even looking at it from the graph, you approach it from the left, you approach x from the left, and also you approach it from the right. In this case, you can see that f of x approach the same value, which is 0.5. Good. And be aware that the graph has a hole here to show us that our function is not defined at x is equal to 1. But it's not a problem because we are testing the behavior of the function around 1, not at 1. So we are not interested at 1 what happens as x is equal to 1. We are studying around 1. That you should take it as a point. So what do you see with this example? We found that f of x gets closer as close as possible to 0.5 as we take values of x which are close and close to 1. And in a notation form of the limit, we normally say the limit of f of x is 0.5 as x goes to 1. So this is how we write it in a notation form, one of the notations that we use for the limit. So bear that in mind. And in an informal definition, we can say in a more general sense, instead of picking the point 1, we can say the limit of f of x is L as x goes to a. So in this case, we are looking at a general arbitrary point a, and also we are looking at another arbitrary point L. And we can say the limit of f of x as x approaches a is equal to L. That's another way to put it. And keep in mind that we are looking at the behavior of the function in the neighborhood of x is equal to a, not at x is equal to a. So we don't want to know anything about what happens as x goes to a, but for the limit we are interested in the neighborhood of x is equal to a, and then start the behavior of the function. That's one thing to take. And another way to put the notation, suppose you are given the normal notation now that you are now familiar with. That means the limit of f of x is L as x goes to a is the same as saying f of x goes to L as x goes to a. Or you can say f of x approaches L as x goes to a. That's another way to say it. So you can look at that. So since we are looking at in the neighborhood of x which is equal to a, we are not looking at x is equal to a. We don't need the function to be defined at x which is equal to a. The only thing that we want to study the behavior around x is equal to a, not at x which is equal to a. So bear that in mind. And that is emphasized by this example of the 3 graphs that we have. So suppose you have these 3 graphs, and suppose that the value of the function at each of, or the value of the function on all the 3 graphs is the same, except at one point at x which is equal to a. For the first graph at x is equal to a, we can see that the value is defined and the value is L of the function. But for the second graph at x which is equal to a, we can see that the value of the function is not defined, or the function is not defined at x which is equal to a. For the third graph, we can see that the function is defined at x is equal to a, but the value is not L. Some other value somewhere here which you can say some value smaller than L. But in all these three cases, we don't need to know what happens at x is equal to a, but we want to study in the neighborhood of x which is equal to a. That means when you get closer to a from the left and when you get closer to a from the right. So you can see from the three graphs, even if you start with the first one, suppose you start with the value of x that is far from a, and then you take the value of x as you get closer to a, you will find that the value of the function gets closer to L. And then you go to the next, you get the value of the function, you find that the value of the function gets closer to L. Now we are approaching from the right. Suppose we are approaching also from the right. Take a value of x that is greater than a, and then find the value of the function and find that the value of the function is a bit bigger than L, and then take a value from the right which is closer to a this time. You find that the value of the function approaches L also. So the same behavior will be observed if you try here, the second case, and then the third case. You will find that the behavior of the function as x approaches a it gives one value which is L. So we'll say in all the three cases the behavior of the function or the values of the function approach L as x approaches a. In all these three cases, that's one thing to take, that we are not interested at x is equal to a, but we are interested what value can we guess of the limit as x approaches a from the left and also from the right, or as x approaches a. So that's the main thing that you should take from these three cases. So now let me give you just 2 minutes to work the limit of this function as x goes to 0. So you have your function here, then you can, but it will take you a long time to plot this function. So just use the table like I did. Try with the table and then look at the values of x which are less than 0 in this case, because x approaches 0 in this case. Start somewhere with the values which are less than 0 and then approach 0 from the left, and also start somewhere with values which are greater than 0 and then approach 0 from the right. Then study the behavior of this function and then come up with the conclusion. Pause the video here, don't go to the next step. Be honest to yourself. Just work it out for 5 minutes, then come back to the video and check what you get. What you should get after doing that, you should get something like this. Should arrive at something like this. You may not have used the same values of x as we did here, where we started from 1 or minus 1, depending whether you are on the left or right. And then we approach 0. You can see we are getting closer and closer to 0, either from the left or right. But as we do that, look at the function. That function approaches 1. That's the good news. As we take those values of x, plug them into the function, and then evaluate the function, you find that the values that we get from the function, they approach 1, either from the left or right. Then we can make a guess that the limit of f of x is 1 as x goes to 0. And here be careful that our function here is not defined at x is equal to 0, because we are dividing by x here, and you can see even from our graph we have a hole into the graph here, so to show that the function is not defined. But we don't mind that. What we want to see the behavior of the function as we approach 0, not at 0. So as we approach 0, the function approaches 1. That's the guess that we are taking. So take that. So what you learned today, you used the table to be able to guess the limit from the table by looking at the values of x as you approach some point, let's say a, from the left and also from the right. And then we kind of concluded that if we can have the same value as we approach from the left and the right, then the limit exists. But if we can have two different values, the limit will conclude that it does not exist. So that's what you learned today. You also learned to arrive to the same conclusion, but now using the graph. Try to look at it graphically, and then you arrive to the same conclusion of the limit. So this is where we stop for today. And tomorrow we'll start with one-sided limit. That means we'll look at the left hand side of x is equal to a, and then study the behavior of the function, and also look at the right hand side separately, and then come up with conclusion. Go and read about that so that tomorrow you are ahead of us. Thank you. So it could be tomorrow next time, but thank you for listening to this, and then let's meet tomorrow or next time. Thank you.